Welcome back to the Deep Dive. We're the place you come to get complex topics broken down fast. And today, well, we're tackling something really complex. We're looking at AI systems so big, so intricate, that debugging them actually requires bringing in another AI.
It sounds a bit strange, doesn't it? But that's kind of the reality with modern AI infrastructure. We're talking these huge racks
Yeah.
just packed with cutting-edge GPUs, and the amount of data they spit out during validation is just staggering.
Right, and if you've ever been near the process of qualifying these beasts before they hit the data center floor, you know that data isn't neat and tidy.
Oh, definitely not. It's an ocean, really. Telemetry coming from everywhere, and in, well, massively different formats. It's all over the place.
Exactly. You've got like in-band diagnostics coming right off the OS, maybe Linux or Windows, and then right alongside that, you've got out-of-band data, stuff from the BMC, the baseboard management controller, or maybe other proprietary management layers.
Yeah, and that mismatch, that heterogeneity, it immediately throws up this huge challenge for diagnostics. How do you even begin to standardize?
It's a real headache. The engineers who developed the solution we're digging into today, they had this perfect metaphor: fight fire with fire.
It really fits. Your AI systems are creating this log complexity, this data inferno, that's just too much for human teams to handle efficiently, especially at scale. So what do? You use AI itself, specifically large language models, LLMs, to, fight back against that complexity.
So that's our mission for this deep dive. We're unpacking a very practical framework, something developed by Microsoft that uses LLMs to assist with this. And crucially, this isn't just some research paper idea.
No, this is battle-hardened stuff. It's actually been adopted by the Open Compute Project, OCP. So it's out there, open source, for the industry to use.
Right, a tool designed specifically to automate log analysis for these big AI GPU systems and data centers. The goal: make testing and debugging way, way more efficient. We want to show you how really experienced engineers are, taking AI and actually using it in their day-to-day technical work, solving problems that used to take weeks, maybe even longer.
And that starting point, the data heterogeneity, it's key. There's been some progress, sure, on standardizing out-of-band data collection. You see some movement there.
Yeah, okay.
But the diagnostics you get through the OS, through all the platform components, the in-band stuff, still kind of the Wild West. There's just not much consistency.
So this framework is like an intelligent layer sitting on top of all that mess.
That's a good way to put it.
Yeah.
It provides interpretation, intelligence, above those diverse, messy inputs. It's a practical engineering response to a very real problem.
Okay. Let's set the stage properly then. Before we get into the nuts and bolts of the AI solution, we need to understand the pain. What were the actual real-world problems that made this level of automation, necessary? The source material really leans on experience from high-volume deployments, mentioning things like the GB200 rack scale solutions. These weren't just servers anymore.
Right, it's a whole different ballgame. And the core issue isn't just complexity in one box. It's complexity timescale. Massive scale.
Okay.
Think about deploying thousands of these nodes. Even if you have a component with a super low failure rate, let's say 1 in 1,000.
Which sounds great on paper.
Yeah, but when you've got thousands of nodes, that low rate suddenly means dozens of racks are having problems. It becomes a major operational headache. The team at Microsoft really zeroed in on 3 main areas where debugging just became incredibly painful, especially with volume and these high-end accelerators involved.
All right, let's break those down. Where do we start? Rack level.
Yeah, let's start at the top, the whole rack. Because when a rack goes down, it's rarely simple. The first big headache they highlighted was rack-level connectivity issues.
Okay, and we're not talking about someone unplugging an Ethernet cable here, are we?
No, definitely not.
Yeah.
This is the really high-speed, often proprietary stuff. Think about the back-end interfaces, especially the scale-up technologies within the rack itself. The connections linking GPUs to GPUs, nodes to nodes, with incredibly tight latency requirements.
Wow, yeah, that sounds like a nightmare to debug. You've got proprietary firmware, dozens of high-speed links needing perfect signal integrity.
Exactly. And then you layer on the inter-rack scale-out technologies too, how these racks talk to each other across the cluster fabric. Trying to debug intermittent failures on these high-speed, often proprietary links, especially when it only happens sometimes at scale, it's incredibly challenging.
So you're coordinating firmware versions, physical connections, everything generating its own logs.
Precisely. It's often a systemic failure, not just one component dying. And finding that root cause, that needle in a haystack across maybe dozens of different log streams, it's just a monumental task for a human.
It shifts the problem entirely. It's not just
Oh.
find the broken part, it's correlate across multiple variables. Okay, let's drop down a level. Headache number 2, node level power. Sounds intense.
It definitely is. The second major pain point was around node-level power envelope scenarios, specifically trying to debug the absolute worst-case power spikes.
Because these modern accelerators, GPUs especially, they just consume enormous amounts of power, right?
They're power monsters.
Right.
Which are incredibly high TDP, thermal design power, and EDP, electrical design power. Debugging these scenarios is tricky because the failure is often really transient. It happens in a microsecond, tied to a sudden peak demand across the system.
That makes total sense.
Yeah.
You're not just checking if the power supply works. You need to know if the entire node, all its components, can handle that absolute peak moment when everything draws maximum current simultaneously. Getting that right requires super fine-grained tuning.
And the debugging itself gets really low level.
Yeah.
You often need to dig into logs tied directly to the power delivery devices themselves, comparing their behavior against their design specs.
Okay.
So if some tiny component on the power delivery board doesn't quite meet its expected parameter during a millisecond peak load, you need logs that can instantly show that deviation and correlate it back to the component's datasheet, its specification.
Which, if you don't have automation...
Engineers are literally spending days, maybe weeks, manually digging through low-level cell logs, trying to cross-reference them against PDF datasheets. It's just a huge time sink, incredibly inefficient.
Okay, and the third headache. This one sounds almost more frustrating because it can pop up later, even after things seem stable. Performance variations.
Exactly. Performance variations. This is often what the end user or the customer actually sees. As the software stack evolved, new AI models get deployed, new frameworks come out, they started seeing unexpected dips or variations in performance. Throughput, latency, things weren't consistent.
It's the ultimate moving target, isn't it? The hardware might be fine functionally, but the workload changes and suddenly it's not optimal anymore.
Precisely. And this meant they often had to go back and do hardware tuning or optimization after deployment. It wasn't enough to just pass the initial functional tests. The systems had to be continuously tweaked and validated against these evolving real-world workloads, which of course means more debugging, more validation cycles.
So these 3 killers, systemic connectivity issues at the rack level, those super transient power spikes at the node level, and this moving target of performance tuning, they all just generate these mountains of log data.
Mountains. And trying to tackle that manually was just crippling the engineering teams. That's really what forced their hand, why they started looking seriously at applying LLMs to speed up the triage and analysis. It became a necessity for efficiency.
Right. You reach a point where the complexity generated by the system outstrips human capacity to analyze it effectively. So this brings us to the framework itself. How did they structure this LLM-assisted approach? It sounds like a multi-stage process layered onto the existing test cycle.
Yeah, it's quite structured. They designed it to be a sort of sophisticated defense system, something applicable across all those problem domains we just talked about, connectivity, power, performance. The idea is to standardize the process of diagnosis, even if the underlying data, the logs, are totally different.
Okay, so where does the process begin? Seems logical it would start with setting expectations.
Absolutely. Stage 1 is crucial, defining test cases and error signatures. The whole automation hinges on this. You need high-quality inputs.
So the engineers have to be really specific. What does good look like for this test run? And maybe more importantly, what specific error messages or log patterns mean failure?
Exactly. You need those clear definitions. Then, following that, they set up trigger scenarios.
These are the actual tests designed to provoke those failures, right? To stress the system in just the right way.
Precisely. They're designed to catch issues, but also to help classify and categorize them intelligently. So if you're testing power delivery, the scenario needs to be crafted to actually try and hit that peak EDP spike. You want to make sure if a weakness exists, you trigger it and log it reliably.
Okay, definition set, triggers deployed. Now we hit the data pipeline itself. Step 3 sounds critical. Log pre-search treatment. You mentioned this is where the messy inputs get cleaned up. Why is this so vital before the AI gets involved?
Simple mantra. Garbage in, garbage out. You just can't point an LLM or even a fast search engine at raw, unsynchronized logs full of proprietary codes and expect good results. This pre-treatment step is where you turn that, well, toxic waste into something usable, something the AI can actually understand. We'll definitely need to drill down into this part more.
Agreed. So data cleaned. Now we get to the core comparison.
Right. Step 4, log search and comparison. This is where the system takes the logs from the run that might have failed the suspected log and
Hmm.
compares it against a baseline, a known good log from a successful run.
And this comparison is where the AI really adds the secret sauce.
That's where the big leap in efficiency happens, yeah. After that search and comparison, there's post-search treatment and log analysis, basically cleaning up the findings and synthesizing them into something digestible for the engineers.
Okay, makes sense. But then there's this other mechanism you mentioned, the stop-on-fail mechanism. This sounds strategically really important. Talk about the efficiency gain here. Why is stopping a test early so critical?
Oh, it's huge. We're talking potentially millions of dollars saved in wasted compute cycles and engineering time. The team was clear. They just couldn't afford to let unique, failed scenarios keep running for hours or days.
Right.
Imagine a really complex validation test, maybe stressing multiple racks, scheduled to run for, say, 72 hours. If unique failure happens just 2 hours in, but the system keeps chugging along for another 70 hours before maybe crashing completely.
That's 70 hours of completely wasted machine time, energy, everything. And 70 hours before an engineer even gets notified to start debugging.
Exactly. So if this framework can quickly spot that unique, known bad failure signature, triage it, grab the necessary logs right then and there, it can halt the run immediately. No wasted cycles. And the engineer can start debugging right away. It fundamentally shifts things from batch processing failure analysis way after the fact to almost real-time active intervention.
That's a paradigm shift. So the final stage is getting that info out.
Yep. Notifying the systems engineer quickly. And not just saying it failed, but giving them ready-to-use logs in that initial AI analysis. The whole point is maximum efficiency for that highly skilled, highly paid engineer. Give them a focused data set, not a multi-gigabyte log dump, so they can make the critical calls immediately.
Okay, let's really get into the weeds now on that data preparation. Turning that chaos of logs you mentioned, over 50 firmware components alone, into something the AI can actually work with. That sounds like the foundation this whole thing is built on.
It absolutely is. It's an
Yeah.
insane volume of data coming off these racks, especially during stress testing, power cycles, updates. The first critical step to impose order is defining the error signature file.
How do engineers even begin to do that across so many different logs and components? BMC logs, OS logs, redfish events?
They have to get granular. The test engineers specify exactly which log file types are relevant for a given test. Are we looking at BMC cell logs this time? Redfish events? Maybe kernel messages, debugs in Linux, or the system event log in Windows.
Yeah.
And within those files, they define the signatures. But critically, it's not just about defining bad signatures. They also define what to ignore. They build whitelists.
Ah, that's smart. So you're telling the system up front, look, I know this specific warning message pops up all the time. It's harmless. Don't flag it. Don't waste the AI's attention or context window on it.
Precisely. You're carving away all the known benign noise right at the start. But just as important, they also define good signatures.
So things that must be present for the run to be considered successful.
Exactly. Maybe it's a specific line confirming the PCI configuration completed correctly for every single GPU in the node. Or maybe a log entry showing the OS successfully entered its high-performance power mode. If one of these required good signatures is missing, even if there are no explicit error messages.
The run is still flagged as a failure. That's proactive. It's not just looking for errors. It's ensuring necessary conditions were met.
It's a much more robust way to validate.
Right.
So, okay, we've got our targets to find the good, the bad, the ignore list. Now we hit that big technical hurdle, the log pre-search treatment,
Yeah.
the data cleaning. You mentioned timestamps earlier. That must be a nightmare.
Yeah, different clocks all over the system.
It's enemy number one for trying to correlate events. So the first task is timestamp normalization. You've got logs coming from the BMC, the OS, maybe applications, firmware. Their clocks can be wildly out of sync, especially during boot up when the main system clock might not even be set correctly yet by NTP.
Right.
If the BMC log says something failed at 2 a.m., but the OS log shows the consequence at 4 a.m. because its clock was off, trying to connect those dots manually is painful, and automated correlation is impossible.
So the system has to figure out those time differences and basically shift everything onto a single consistent timeline, create an accurate chronological map of what happened when.
That's fundamental. You have to
Yeah.
do that first. The second step here is interesting. It's an engineering trade-off. Data structure conversion. So lots of modern logs are nicely structured, right? JSON, maybe XML, which is great for machines to parse programmatically.
Yeah, sounds like clean data.
It is. But the high-speed search technology they used underneath this framework, it's heavily optimized for simple line-based text searching. Think grep on steroids.
Oh,
So to make that initial search super fast across massive files, they actually convert the structured JSON or XML into a flat, single-line format, often just comma-separated values, CSV.
wait, really? They flattened structured data back into basically a long text string? That
Yeah.
sounds backwards. Isn't JSON supposed to be better?
It is better for many things. This is a really pragmatic choice. For the initial brute force search across potentially terabytes of logs, speed is everything. By flattening a JSON object related to a single event into one long line, you ensure all the relevant data points for that event are together, and the line-based search engine can rip through it incredibly quickly.
So they're prioritizing raw search throughput at this stage over maintaining the original data hierarchy.
Exactly. It's a classic real-world engineering decision. Optimize for the bottleneck. You can always reconstruct or reference the original structure later if needed, but for finding that needle in a haystack quickly, line-based is faster at massive scale.
That's a great insight. Okay, what else happens in pretreatment?
Another absolutely essential piece is decoding. A lot of the really critical low-level logs aren't human-readable text. Think proprietary superlogs or CPRD critical platform record data, or maybe raw I2C bus dumps. They're often binary or use specific vendor encodings.
Stuff you can't just grep for.
Right. So the framework needs a library of specific decoding tools. It has to run these tools on those binary logs to translate them into plain text, making them human-readable and, crucially, searchable by the text-based engine and understandable by the LLM later.
You have to turn the hieroglyphics into English before the AI can read it.
Basically, yeah. Without that decoding step, the system would be completely blind to some of the most important low-level hardware events that might be the root cause.
Makes sense. Anything else in the coding pipeline?
There's one more optional, but often really helpful step: log convergence.
Okay.
This involves taking logs from different sources, say the BMC, the OS, maybe a specific application log, and merging them together into a single unified stream, all ordered correctly by their normalized timestamps.
Ah, so you create one chronological story of everything that happened across the different system layers.
Exactly. It makes it much easier for an engineer later to follow a chain of events. You can see the power fault reported by the BMC, then the resulting kernel panic in the OS log, all interleaved in the correct time sequence within a single file view. It really helps connect the dots for root cause analysis.
Okay, that whole pre-treatment phase sounds incredibly involved, but absolutely necessary. You've got your error signatures, you've normalized timestamps, flattened structures, decoded binary data, maybe even merged logs. Now the data is finally ready for the intelligent part.
Now it's intelligence ready. We move into the actual search and comparison loop. And this is where things really diverge from just traditional log searching, where the AI component becomes transformative.
So how does it kick off? Still some traditional searching first.
Yeah, the initial phase is still about speed and efficiency using classic methods, the initial log search. The tool takes those defined error signatures, runs them against the cleaned, pre-treated log files, and importantly, filters out anything that matches the whitelist we talked about.
Okay, filtering out the known noise.
Right. This generates a first-pass list of suspected error matches. And crucially, at this stage, it also double-checks that all those required good signatures are actually present in the logs. If any are missing, remember, that's a failure condition too.
So standard filtering and verification, but you said the comparison part is where the LLM really shines. How does that work?
Yes, this is the core of the added intelligence. The good log versus suspected log comparison. This whole mechanism came about because the engineers found that even with good filtering, sometimes telling the difference between a genuinely new significant failure and just a minor harmless variation from the baseline. It takes judgment.
Human-like judgment.
Exactly. And they had this realization. They literally said, AI knows better than our tool in some of these ambiguous cases. There are limits to purely rule-based algorithmic logic. You need something that can handle nuance, which LLMs are surprisingly good at.
That's a fascinating admission. So how do you compare a potentially massive bad log file against a good one effectively?
Before the actual comparison happens, there's another vital normalization step. Log normalization specific to the comparison task.
Okay.
Think about it. Even between two runs of the exact same test, one good, one bad, there will be hundreds, maybe thousands of lines that are different just because of trivial things. Timestamps would be different, obviously. Memory addresses might change slightly. Maybe the test ran on node #3 this time instead of node #2. So you see GPU or tag 3 instead of GPU check 2 in the logs.
Right. Tons of differences that don't actually indicate a problem. They're just context.
Exactly. So this normalization step tries to surgically remove or abstract away those obvious non-concerning differences. You want the comparison to focus only on the meaningful structural or functional deviations, not noise, like which specific GPU instance was involved.
Got it. Filter out the circumstantial differences. Then what?
Then they actually apply a classic fuzzy search technology first. This is done locally, it's fast. Fuzzy search is good at finding lines or blocks of text that are similar but not identical. It helps cluster related differences together quickly and can identify large chunks of variation.
So use the faster, dumber tool first to get a rough idea of where the differences lie?
Pretty much. But the output of that fuzzy search, the set of differences, can still be enormous. Way too big to just feed directly into an LLM, given their context window limitations.
Yeah, the infamous context window size limit. How do they get around that if the diff is huge?
They use a technique called chunkization. They take that large set of difference data generated by the fuzzy search and break it down into smaller, manageable chunks.
Okay.
These smaller chunks are then fed, often sequentially, to a locally hosted RLM server, a smaller, more focused language model running on their own infrastructure. The AI's specific job for each chunk isn't to understand the whole log, but to perform a high-judgment qualitative analysis on that specific chunk of differences.
So its task is looking at this small piece of the difference. Does this look like a real bad error, or is it likely just a harmless variation that the normalization and fuzzy search didn't fully catch?
That's precisely it. It's applying nuanced judgment to focused pieces of data. It's a really clever way to scale the analysis. You use the fast local tools for the bulk comparison, and then you bring in the more computationally expensive, high-judgment LLM only for the ambiguous parts, the key differences identified by the fuzzy search broken into manageable pieces. It's smart resource allocation.
That makes so much sense. It dramatically changes the time it takes to get to a meaningful answer. What happens after the LLM has looked at the chunks?
The final step in this loop is the post-search cleanup. The results, both from the initial fuzzy search and incorporating the judgments from the LLM on the chunks, are all brought together. They group similar findings and perform deduplication based on the fuzzy search clustering and the LLM's verdicts.
So you end up with a clean, concise list.
That's the goal. A clean, final list of unique, confirmed failure signatures or significant deviations ready for the next stage of analysis without all the noise and redundancy.
Okay, so the system has done an incredible amount of work. Filtering, cleaning, comparing, using AI judgment to confirm real issues. But just knowing what failed isn't always enough, right? Engineers need to know why. How does the system help with root cause identification before it sends out that notification?
This is where it gets really cool, I think. This is where the system starts to connect the dots, linking the raw failure data it just confirmed to broader knowledge. It uses contextual knowledge search, essentially retrieval augmented generation, or RAG.
RAG, okay. So for that final clean list of confirmed errors, it goes searching somewhere else.
Exactly. It queries two key knowledge bases simultaneously.
What are they? What kind of info is in there?
First, the internal bug database. This has all the historical failure data bugs that have been seen before, triage notes from engineers, known failure modes, maybe links to specific code revisions or hardware batches.
Okay, so learning from past mistakes.
Right. And second, critically, the vector database used for the RAG component. This is loaded up with all the deep technical documentation. We're talking component specifications, official troubleshooting guides, detailed rack architecture diagrams, internal system knowledge, best practices, all that institutional knowledge turned into searchable vectors.
Wow. So it's not just looking at the logs from this failure. It's instantly comparing this failure against all past failures and against how the system should behave according to its design docs and specs.
That's the power of it. It takes the clean log fragments showing the current failure, combines them with relevant historical bug data and relevant snippets from the technical documentation pulled by the RAG system, and feeds all of that context together into the LLM for one final step.
And what's the LLM's job this time?
Its role shifts from filtering and judgment to synthesis and suggestion. It performs a final AI analysis and summary based on all that combined input. And importantly, it provides suggested next steps, or what the source material brilliantly called fishbone paths for root cause analysis.
Fishbone paths, I love that. Like the Ishikawa diagrams for root cause analysis. So the AI is actually suggesting potential causal chains for the engineer to investigate.
Exactly. It's like the AI is saying, okay, based on this specific error signature appearing in the log and the fact that bug #1234 showed similar symptoms last year, and the spec sheet for component XYZ says this parameter should be different, I suggest you investigate component Y and Z first, or check configuration setting Q.
That's a game changer. It takes the engineer from, okay, here's an error, now I have to spend 2 days digging through wikis and datasheets to figure out where to even start
To having an AI provide intelligent, prioritized starting points immediately. It drastically cuts down that mean time to diagnosis, MTTD. It focuses the human expert's valuable time on the most likely causes first, based on a huge amount of synthesized information.
And presumably, the system learns.
Oh yeah, that's the intelligence evolution part. When the engineer follows one of those suggested fishbone paths and confirms, yep, that was the root cause, that feedback gets looped back into the system.
So the LLM learns which suggestions were actually helpful, which paths led to successful diagnoses.
Exactly. It refines its knowledge, gets better at correlating symptoms with causes, and improves its suggestions for the next time a similar issue occurs. It's a continuous learning loop.
Which all leads to that final step, rapid notification. You mentioned that anecdote about the engineer mowing the lawn.
Yeah, the goal is speed and precision. Get a notification out fast, but make sure it contained high-quality, pre-analyzed data, the confirmed error, the context from the databases, the suggested fishbone paths. So that engineer, even if they're not at their desk, maybe it's the weekend, they can look at it quickly, understand the likely scope, and make a critical decision right away. Like, do we need to stop other tests? Do I need to drive in?
Because the cost of letting a bad test run continue or delaying the fix is just enormous in terms of energy, machine time, and lost development velocity.
Absolutely. Stop on fail, provide immediate context. It maximizes the value of every single engineering hour. This is practical AI making a real difference in complex system debug.
Okay, this framework sounds incredibly powerful in theory. Let's make it concrete. Let's talk about the real-world wins, the aha, moments where the system really proved its worth. These case studies really highlight how this OCP-adopted solution tackles problems that were just killers for traditional methods, especially at the rack level.
Yeah, these examples are great because they focus on those really tricky, intermittent, low failure rate issues, the kind of thing that's almost impossible to reliably reproduce in a controlled lab setting, but cause havoc in large-scale deployments.
Okay, let's start with case study 1. The faulty power delivery device.
This sounds like that classic nightmare scenario. A rare failure, but when it happens, the impact is huge, and you can't easily make it happen on demand.
That's exactly what it was. They had an issue with a specific device on the power delivery board inside the node. The failure rate was super low, maybe fractions of a percent. It only seemed to fail under very specific transient high-power conditions that would only pop up occasionally during the really intense volume validation tests.
But when it failed,
Node wouldn't boot. Dead in the water. Huge impact. But trying to reproduce that specific spike condition on a specific node in the lab, good luck. There's too much variability across the components, even within the same batch.
so how did the framework nail this one down so quickly? They relied on the granularity of the error signatures they defined, specifically looking at the low-level cell logs from the power delivery subsystem. Once the pre-treatment cleaned those logs and the search and comparison flagged the signature.
That RAG system kicked in.
Exactly. The system automatically correlated the specific parameter that was failing in the log with the actual engineering specification for that device, which was stored in the vector database. The AI analysis instantly highlighted, hey, this device's behavior during that power spike is deviating significantly from how it's supposed to behave according to its own datasheet.
That immediate correlation is the magic. Without the system, an engineer gets that cryptic cell log error, then has to manually find the datasheet for that specific chip, figure out which parameter it relates to, compare the values.
Yeah.
It could take days. The system did it almost instantly.
Right. The triage was incredibly fast, pinpointing the device-level issue immediately, and the impact went way beyond just fixing that one node. The crisp, data-driven evidence gathered by the framework was so compelling that it directly influenced a major design change recommendation for the entire power delivery board. They actually changed the bill of materials, the BOM.
Wow, hold on. So a software diagnostic tool using AI analysis of logs led directly to changing the physical list of components used to build future versions of the hardware.
Yes, that's a massive win. You're preventing potentially thousands of future failures across the entire product line based on an intelligent diagnosis made early during volume testing. That's huge leverage.
And I bet they could share that finding too.
Absolutely. They shared the fix, the updated diagnostic signature, everything, with teams working on other parallel hardware configurations using similar components. It prevented the same problem from biting them later. That's the power of finding these things early and systematically.
Okay, incredible example. Let's look at case study 2. This one was about networking, link-related failures. High-speed interconnects are always tricky.
Definitely. This involved persistent failures during link connectivity tests, and it covered both proprietary scale-up links within the rack and standard network protocols used for scale-out between racks. These tests are notorious for spitting out logs that are just obscure.
Yeah, you often end up having to manually parse massive vendor-specific debug logs from the accelerator cards themselves, trying to track down things like bit error rates, BERs. It can be a multi-week investigation per incident.
The framework completely streamlined this. First, it was configured to pull the relevant failure signatures not just from standard OS or BMC logs, but directly from those dense, often opaque proprietary debug logs provided by the accelerator vendors.
So it could understand the vendor-specific stuff, too.
Yes, using the appropriate decoders and signatures. Then, it automatically extracted key metrics like the BERs being reported and compared them against the expected thresholds defined in the engineering specifications stored in the REG database.
Okay, so again, automatic comparison against the spec. What was the big strategic win here, getting this clean data so early?
It gave the Microsoft team concrete, undeniable data points. This allowed them to go back to the accelerator vendors with very specific feedback. They could essentially say, look, we are seeing these specific BER patterns on your links under these conditions. Your current diagnostic logs are missing critical information X, Y, and Z that we need for automated analysis and faster root cause.
Ah, so they used their internal analysis capability to push for better diagnostics from their own suppliers. That's really interesting, driving improvement up the supply chain.
Exactly. It helped improve the quality of diagnostics industry-wide, or at least for their key partners. And internally, the AI analysis was also crucial.
Oh.
It was able to look at all the different link failure signatures it was finding and intelligently group them. It could subcategorize multiple different underlying issues that were all just presenting as a generic link test fail. Maybe one group was related to signal integrity, another to a firmware bug, another to a specific cable type.
Getting that clarity early is huge.
It is. And crucially, it also helped them quickly distinguish between a real failure in the product hardware versus sometimes just a defective test fixture or a bad cable being used in the validation setup itself. Imagine wasting weeks debugging a product failure that was actually just caused by a faulty piece of test gear.
Oh yeah, that happens all the time. Preventing that kind of wasted effort is a massive efficiency gain in itself. These case studies really paint a picture of how practical AI can solve extremely complex, expensive problems in hardware validation.
They really do. And I think the most important part, the key takeaway the engineers wanted to emphasize, is that this powerful framework, born from solving these really tough rack-level debug challenges, it's not locked away.
Right, it's open source. This isn't just a Microsoft internal tool anymore.
Exactly. The log analyzer code, as it's called, has been adopted by the Open Compute Project, OCP. It's available up on GitHub in the Microsoft Log Analyzer repository. Anyone wrestling with similar large-scale system validation and debug issues can potentially use it, contribute to it.
So it's experienced engineers effectively sharing their battle-tested tools to help lift the entire industry.
That's the philosophy behind it. The team is actively encouraging industry adoption. They want feedback. They want feature requests. The core belief seems to be that if everyone gets better and faster at diagnostics, especially with these increasingly complex AI systems, then the whole ecosystem develops faster. A rising tide lifts all boats.
And this whole effort also sends a pretty clear message back to the hardware vendors, right? The silicon companies, the system designers.
Absolutely. It's a clear call to action. The speakers who developed this were very specific. Vendors need to think about how their components generate logs. They need to provide logs and diagnostic tools that are easier to digest, not just by humans, but by automated systems like this one, both traditional line-based search and these more advanced AI analysis methods.
They mentioned specifically needing clearer differences between good logs and bad logs.
Yeah, making sure that when something fails, the resulting log output is meaningfully different in a way that automated comparison tools can easily pick up on, without getting drowned in trivial variations. It's about designing for diagnosability from the start.
It pushes the standard beyond just does the hardware function to can we efficiently diagnose and validate this hardware at scale using intelligent automation?
That's the shift. It's about enabling this next level of automation throughout the entire life cycle, from development through deployment and validation.
So let's zoom out for a final thought. We've seen how this AI-assisted framework can take log analysis tasks that used to consume weeks of expert human time, like chasing intermittent power faults or complex link errors, and compress them dramatically, providing contextual insights almost immediately. If this kind of diagnostic intelligence becomes the norm, how much faster does hardware innovation actually get?
That's the really provocative question, isn't it? When the bottleneck of manual log analysis and root cause diagnosis is significantly reduced or even eliminated for many common issues, does that free up engineering brain power to focus purely on the next generation of design challenges? And what's the next step for AI in this cycle?
Right. If LLMs can already move from just finding failures to suggesting intelligent fishbone paths for root cause analysis and feeding that learning back into the system, what's the next task for critical thinking AI in the hardware development process? Is it predicting failures before they even happen based on subtle patterns in early testing? Is it suggesting design modifications proactively?
That ability to move from reactive diagnosis to proactive prediction and potentially even automated design refinement based on log analysis, that feels like the powerful frontier this kind of technology is really starting to open up. It's an exciting and maybe slightly daunting future for hardware development.
A future increasingly driven by AI, analyzing the data generated by AI systems themselves. That's our deep dive into the Microsoft Log Analyzer framework. Thanks for joining us.